Okay, we continue on the shallow foundation design. Okay. Okay. As we know that shallow foundations apply to pad, strip, and rough foundation, and some provision may be applied to deep foundations such as a caizon. Okay. So under limit state, uh, so there are some conditions, okay, where we may look, okay, under the shallow foundation, okay, which is loss of overall stability, bearing resistant failure, failure by sliding, ground and structure combined failure, structural failure due to foundation movement, excessive settlement, excessive heave, unacceptable vibrations. Okay. So this is an example, okay, of the some of the ULS and some of LSS, okay, uh, which is on the loss of stability, bearing failure, sliding, structure failure, combined failure in ground and structure. Both need to be considered. Okay, it's been reported by Scarpelli. Okay. So design and construction consideration must be considered when choosing the depth of the spread foundation, okay, due to the climate effect, sinkage or swelling of clay, frost damage, case nearby structure, services, soluble material, ground, water table, and inadequate pairing stratums. Okay. So design requirement, the design must meet two principal requirements of the limit state. Okay. First one is capacity insufficient to support load. Second, avoiding excess settlement, which might lead to a loss of function. Okay. So the limit state is, yeah, this is what we have discussed previously. Okay. The concept related can be shown in figure below. Okay. So this is just an example uh, to define or uh, to define what we call as the conditions, okay, under the ULS, okay, and also the condition under SLS, okay, which is the limiting settlement while the bearing capacity. Okay. So normally in design, we in construction, we may refer to the working loads. Okay. So design requirement, okay, one of the following design methods must be used for shallow foundation. Okay, the first one is the direct, carry out separate analysis to each limit state and both ultimate and serviceability. Okay, indirect, use comparable experience with result of field and laboratory measurement observation. Prescriptive, use conventional and conservative design rule and specify control of constructions. Okay. So normally in our case, okay, we may refer to the direct approach. Okay, we carry out the analysis under ELS and also may include on the SLS as well. Okay. So the ultimate limit state, it implies the application of partial effect safety to action or effect of action to obtain the design action and to geotechnical parameter or resistance to obtain the RD design resistance. Okay, so that is the goal by using the Euro codes. Then for the service limit state, okay, need to check for the CD is the limiting design value of the effect of an action. which is the CD. So see, I have a call. Wait. Okay, the design action can be represented by, okay, this is the term that we may, the equation that we may use later. Okay, so I just uh, describe in a general. Okay, then we may go for the example to uh, identify what is the parameter that need to be included, okay, in order to obtain the design action. Okay. So in here we have a characteristic permanent loads, okay, characteristic variable loads, factor for combination value of variable loads, okay, partial factor safety for permanent loads, partial factor safety for variable loads. Okay, so direct method, okay, this is direct method that we may use, okay, ULS design approach 1, so we have combination 1 and combination 2, okay. Two are the two condition, either drain or undrain. Okay, so the difference between uh, the what we call as the Euro code and the British standard. Okay, so if the British standard, they differentiate between the type of the soil based on sand and clay, okay, cohesiveness or cohesive. But in the Euro code, they differentiate between type of soil based on drain and or undrained. So drain, uh, it is more related to the sand, okay, while undrained is more on clay. Okay. So LSS check the performance of the foundations. Okay. So however, for our discussion, we discuss more on the ULS, okay, not the SLS. Okay. So partial factor of safety, okay. So this is based on the uh, what we call as a Malaysian standard. Okay, so uh, then we may try to compare, okay, with the what we call it with the EC7, okay, based on the previous slide. Okay, so you need you if you have time, so you need to compare. Okay, what will be the difference between the Euro codes and also the Malaysian standard. Okay. So A1, M1, and R1. Okay, so this is action, soil, and spread footing for the shadow foundation. Okay, so we have here M2 and M2 based on the location of the problems. Okay, so if located on slopes and embankment, and then we may use the M2 asterisk if other than slope and embankment, so we may use on the M2. Okay? So most our discussion is based on the M2, not the M2 asterisk. Okay? So the bearing resistance. Okay, so BD must be included with of foundation and any backfill above it. Okay, design action BD variable vertical loads, permanent vertical load, supported permanent load, weight of foundation, weight of backfill. So this is to calculate on the bearing resistance. Okay. For some consideration, for drain condition, water pressure must be included as action. Okay, how to apply to the partial factor safety to the width of the submerged structure, since the water pressure act to reduce BD. So it may be considered as favorable while the total weight is unfavorable. Okay. So favorable is in the load that we gain benefits, while unfavorable is the is any weight that we are not favored to it. Okay, for example, failure, uh, settlement, so we consider as unfavorable. Okay. Basically, the soil has to sustain the submerged weight. For the design structure member, water pressure may be unfavorable. Okay. So sliding resistant, this is normally we use for the embankment design. Sorry, for the retaining wall structure. Okay, for the drain condition for the sliding, so we may use this equation. Okay. And for the undrained condition, we may use this equation. Okay. However, I will not discuss on this sliding in sliding resistance in our example. Okay. So some concentration maximum sliding will occur with little movement of RD and RPD, which cause difficulty in mobilizing both magnitude. Remodeling effect of excavation, erosion, and shrinkage passive resistance should be neglected. In some circumstances, the vertical load in undrained condition is insufficient to produce full contact between soil and foundation, though the design resistance should be limited to 0.4 VD. Okay, so this is just an general information, okay, for the sliding problems. Okay, so bearing capacity in drain. Okay, we still use the same equation based on the Mayer-Hoff. Okay. However, the difference between the Euro code and the British standard, okay, or from the Mayer-Hoff, okay, so it doesn't include the depth factor, okay, in the design compared to the Mayer-Hoff. Uh, Based on the convention, based on the British standard, okay, we have the what we call as depth factor. Okay. So we have here shape factor and inclination only. Okay, no depth factor. Okay. So I'm not sure when I refer to the Smith reference book, he also doesn't he also put the comment on this issue on the depth factor. Okay. So we may go through later on the Smith. Okay, right after I complete my presentation. So this is the common NC. Okay, either we can get from the table or we can use this equation to calculate for the for the NQ, NC, or N gamma. So this is for N gamma, NQ. Okay. Then we have the NC, okay, and also N gamma. I guess similar with what approach in the Mayer-Hoff under the British standard. So the final bearing capacity and gamma is difficult to determine analytically, and as it is influenced by the roughness of the base and soil interaction. So in MS7 superseded by N gamma give in NXD, the following expression is proposed. Okay. So this is the N gamma vein equation for the new MS under the MS EN7. Okay. So the sample method give in MSEN 1987, NXD omit depth. Okay, so this is depth, it's not be included, and ground inclinations factor which are commonly found in the bearing resistant formulation. Okay, so no depth and also inclination. The omission of the depth factor is on the side of the safety, but the omission of the ground inclination does not. declination factor does not. Okay, so that is the what difference between the main difference between um, purity standard and also EN standard EN. To determine the ground inclination factor, one of the methods which may be considered is prescribed in the foundation and earth structure design manual will be mentioned in the next topic. Okay, so there will be slightly different between the approach in the EN for the ground inclination factor. Okay, compared to the previous one. Okay. So this is the shape factor. Okay, SQ for rectangular shape and square, S gamma for rectangular shape and square, or we can use this what we call as this graph. Okay, and SC. Okay, so that is for the shape factor. Okay, then this is for the inclination. Okay, where they have a little bit change difference as mentioned in the what we call in the annex. Okay, so then we have the M. Okay, okay, so this is how we may calculate for the M, B, and M, L based on, for example, if they are eccentricity. So they include the eccentricity, okay, in the calculation for the inclination. Okay. For example, if the location of the loads, okay, for example here, okay, so we need to count what will be the MB and also the ML. Okay, so then include in the calculation for the I gamma, where his x in the direction. Okay, so means that if we look on this diagram, okay, so normal discussion, we only discuss on this type of eccentricity, okay, but in this inclination, so we may have an inclination load and at the same time it is have an eccentricity issue. Okay. So instead that the vertical load action should include the weight of any backfill acting on the top of the footing in addition to the weight of the foundation itself plus the applied load carried. This will be explained further in the next section. Okay. Okay, so either we use the calculation or we may use what we call as this chart to get the NC, NQ, and N gamma. Okay, so okay, as we know, the NC okay, is represent the sub equation number 1, okay, and the C value that we should use is the value of the C below the foundation. Okay, and then NQ, okay, is more related to the sub equation number 2, okay, where the gamma that we use, okay, due to the gamma above the foundation's base. And then we have sub equation number 3, which is the N gamma. So the N gamma that we use, okay, or the gamma that we use in the calculation for sub equation number 3 is based on the soil properties below the foundation base. Okay. So we can later on we may discuss on the Smith reference. Okay. Okay. So if they are water, so there will be slight changes. Okay, on the equation. Okay. So we have 3 type of water condition where the water from the base, where the water from the ground to the base, okay, and the water from the base to the width depth of the to the width of the foundation. For example, okay, okay, this is condition number one, where the water located here. Okay, so the condition number two, where the water is located between uh, the base to the depth of the width of the foundation, and condition number three, where the water is far or greater than the depth based on B of the foundation. So it's vital that the appropriate value of unit weight are used in bearing capacity equation. In an effective stress analysis, three different situations must be considered by assuming no inclination. Okay. If the water table is below the foundation plane, the bulk unit weight to be used is the second and the third term of the equation. Okay. So if the water table is at the foundation plane, okay, the buoyancy unit weight must be used in the third term of the equation. Okay. The bulk unit weight should be used in second terms for unit. If the water flow is in surface or above, okay, the effective unit weight must be used in the second and third of the equation. Okay. So that is the for the water condition. Okay. So calculation procedure for shallow foundation on undrained, okay, and drain material. Use limit state design, total stress or effective stress analysis, determine the strength, shear strength parameter or effective stress parameter and unit weight of the underlying. So determine the bearing capacity factor, groundwater level and effective stress analysis. The groundwater table will be give impact to bearing capacity. Ultimate limit state evaluation depends on the type of footing and analysis using design approach one only. Determine the size of the footing initially. Okay, so we have combination 1 and 2 for the design approach 1. Check on stability limit state. The allowable bearing capacity may be used to be downgraded due to the local building code or practice or lower bearing pressure to avoid excessive settlement allowed. Okay. That's the procedure. Okay, so this is for the what we call as direct methods. Means that we use the calculation. Okay. Then we have a indirect method, okay, which is the empirical approach. Okay. So by using the bearing capacity from SPT, is by using the SPT value, so we can determine what is the bearing capacity. Okay. So how to convert N? Okay, but we need to convert first the N, okay, to get the N70. Okay, where we have new 1, new 2, new 3, and new 4. Okay, and then CN. So um, so then we may get the NX, okay, to determine to calculate for the bearing capacity. So bearing capacity from SPT widely used to obtain the bearing capacity of soil directly. May have used for computing the allowable bearing capacity for 25 millimeter settlement. So this is the N value in, that should be used in the equation. Okay. But in our case, we only we may discuss on the example based on the direct method, not based on this indirect method. Just for general information. Okay, then factor F of follow. Okay, so we have uh, the the example for the factor F as follow. Okay. So or we can use the chart to estimate what will be the QA, okay, based on the what we call on the bearing capacity value. Okay, or we can use this formula by using the N 55. Okay. So N55 and 7 is the statistical arrangement average value for the footing in pen zone about 0.5 B above footing base to at least 2 B below. Okay, this is taken into account somewhat formats where Meyerhoff obtained QA and 55 over N70 F2 AD. Okay. So this is the approach by using the for the map uh, foundation. Okay, so in this equation the allowable pressure is for the assumed 25 millimeter settlement. So in general the allowable pressure for any settlement, okay, is delta HCG over delta H naught QE, where delta H is 25 meter and delta Hg is the actual settlement that can be tolerated in millimeters, such as 50 millimeter normally for mat foundation. So for sand, okay, so this is the equation for sand to calculate for the bearing capacity. Okay, allowable bearing capacity QA is complete for settlement checking for delta H equal to 20 millimeter. Okay, then for CPT, bearing capacity for CPT, so this is the equation that can be used to estimate the bearing capacity based from the SPT value. Okay, where QC is the average over depth interval from B half to 1. Okay, 1B below the footing base, the application should be used for dB less than 1.5. Okay, so for cohesion soil and to calculate for the strip and scope foundation, and for clay, so this is the formula to calculate for the bearing capacity from the CPT. Okay, but make sure that the unit should be in kilogram per centimeter square for the QC value. Okay. So that is for the indirect methods. Okay. So now we look on the Smith reference book. Okay. Okay, to discuss on the example for the calculation on the shallow foundation. So you can do a reading, okay, for this shallow foundation. Okay. So bearing capacity of soil, okay. So you can start.
Sorry, Doctor.
Yes.
Sorry, Doctor. This is also in e-learning
Yes,
for
yes, yes.
this book?
Already
Okay.
include. So please refer to your e-learning. Okay.
Okay.
Okay. So it's very useful reference book. Okay, because uh, uh, Smith discussed first on the British on the conventional methods. Okay, so at least when we do a reading on this reference book, so we can uh, recap or resharpening again our knowledge, okay, on the shallow foundation. Okay, so sip circle methods. Okay, this is how the evolution of the bearing capacity equation. Okay, so from the Earth pressure theory, okay, and then they discuss on the slip circle methods, okay, and then on the ultimate plastic limb failure theory, okay, based on the Terzaghi. Okay, this is based on the general shear failure. Okay, so this is the equation based on Terzaghi. Okay, then in here we have okay, so this he also discussed on the and this also show an example, okay, on the British standard calculation. Okay. Okay, this is on the sieve bearing capacity. Okay, so this is discussion on the effect of the groundwater on bearing capacity. Okay, then this is on the Meyerhof equation. Okay, so in the Meyerhof equation, we have a depth factor, okay, which is the d, c, d, q, and d gamma. Okay, okay, then this is shape factor, depth factor. I want to show you. Mm. So yeah, this is the discussion on where we should uh, use the value for the soil properties, okay, for the NQ and gamma and NC. Okay, then okay, this is based on Meyerhof. Okay, okay, this is due to effect of eccentricity and incline loading. Okay, so this is a new in the what we call in the Euro EC7. Okay, designing spread foundation to Euro code 7. Okay, so the design cover in, let me, the term, okay, the code commonly, okay, why the design procedure safety, shape and inclination factor as well. Okay. In here, there's okay, interesting, the depth factor are excluded, okay, in Eurocode 7 without explanation, okay. And for this reason, they are include two from the solution, okay. So Smith also mentioned here, okay, not being included, the depth factor, okay. So they introduced the new one of the inclination with the eccentricity. Okay. So now we look on the example, okay, based on the Euro code and also based on the normal or conventional conventional calculation. Okay. So a continuous footing, okay, is 1.8 meter wide by 0.5 meter deep and is founded at the depth of 0.75 in the clay soil of unit width 20, with Phi is equal to 0 and Cu is equal to 30. The foundation is to carry a vertical line load of magnitude 50 kilonewton per meter run, which will act as a distance of 0.4 from the center line. You take the unit width of the concrete as 24. Okay. First, determine the safe bearing capacity for the footing, taking F is equal to 3.0. Okay. check the Eurocode 7, okay, geo limit state design approach 1 by establishing the magnitude of the over design factor. Okay, so now we look uh, on this example. Okay. Okay. So for the first one, determine the safe bearing capacity for footing. Okay. So because it has eccentricity, so we need to get the E value. Okay. Because we want to calculate for the new B prime. Okay. So to get the E value, so we need to determine what is the P and also the W. Okay. So self weight of the foundation, W is the weight of the foundation, 0.5 times 24 times 1.8. Okay, so 0.5 is the thickness and 1.8 is the wide, is the width of the foundation. Then 24 is the unit weight of the concrete. Okay, so then we get 21.6, 21.6. Okay, so then the weight of the soil on the top of the foundation. Okay, because the soil has been construct 0.75 depth, okay, in a clay. So after minus the thickness of the footing, so we obtain 0.25 thick of a soil layer. Okay, so then we multiply with 20. Okay, and then multiply with 1.8. 20 is the unit width of the soil. Okay, so 1.8 is the width of the footing. Okay, so it is a continuous footing, so we get the value in kilonewton per meter run. Okay, so then the total weight of the foundation is W 21.6 plus 9, so then we obtain 30.6. Okay, so from there we get the value of E, where the P is the magnitude of the load, okay, times 0.4 over 50 plus 30.6 equal to 0.25. That is for the E. Okay. So since E is less is that equal uh, B over 6, okay, the total force act within the middle third of the foundation, then we can use the approach of B prime. Okay, so the effective width of the foundation is equal to 1.8 minus 2 times 0.25. This is the equation for to determine the B prime. So then we get 1.3 meter, okay, for the new B prime. Okay. Okay, so by using the conventional approach, okay, refer the table 8.1. Let me see if we have table 8.1 here. Okay, this one. Okay, so we need to refer to this table. Okay, on the page of 316, eh? Okay. So with the is equal to 0, okay, because it is what we call as a clay. Okay, so then NC is equal to 5.14 and Q is equal to 1 and gamma is equal to 0. Okay, so footing is continuous. Okay, So then we may assume that L is equal to infinity. So SC is equal to 1. Okay, DC is equal to 1.17. Okay. So then by using the formula of the Meyerhof, okay, so safety bearing capacity for the continuous footing, okay, or for the slip footing. So this is the formula. Okay, CNC SCDC over 3, okay, plus gamma Z, okay, and the value for the safe bearing capacity is 75. Okay. Then to get the load safe bearing capacity value, so we may multiply with the B prime, which is 97.5. Okay, so this is based on the conventional approach. Okay. So I guess most of you are familiar with this approach. Okay, then we move to the Eurocode 7. Okay. Uh, okay. So we use the first, what we call as the first combination one. Okay. Uh, Partial factor safety set A1 plus M1 plus R1. Okay. So from the table 7.1, so we doesn't have table 7.1 here. Okay. Because this chapter start at 8.1, and also I have only this chapter 8 and 9 only. Okay. But it is same with the one that I have shared in the slide. Okay. So from the table, we use the unfavorable because we consider it is what we call is a failure condition. Okay. So then we set as a 1.35. Okay. For the permanent, and also for the what we call as for the variable. Okay. It will be 1.5. Okay. So then for the soil, okay, soil for the M1, okay, so we choose the effective cohesions, okay. So the sorry, undrained strength, okay, because this is CU, CU, the value for the M1 is equal to 1.0, okay. And then for the spade footing, which is the R1, okay, we choose as a bearing, okay, which is equal to 1.0. Okay. So design material property, KCU over gamma CU, which is this one, okay, equal to 30. Okay. Okay. Then we start to apply, okay, because for the material we need to divide, and however for the loads we need to we need to multiply. Okay. So design action, weight of the foundation, okay, W. This is what is we have this what we call, we have calculated previously. Okay. So times 1.35. Okay. Then we obtain 41.3. Okay. So then apply load. Okay. P multiply with 1.35. Then we obtain 67.5. Okay. So then for the total vertical force, okay, which is the summation of weight and applied load after it's been multiplied with the uh, partial factor of safety. So we obtain 108.8. Okay. So from there we calculate for the eccentricity, the same procedure, okay, with the previous one, okay, which is the PD over A times EP over PD plus WD. So we obtain 0.248. Okay. So since E less than B over 6, so the total force at within the middle third of the foundation. So the effective width of the footing is 1.8 minus 2 times 0.248, okay, which is equal to 1.3. Okay. So then we may calculate for the design resistance. Okay. So the NC should be determined first. Okay, with the I guess there will be no difference in terms of the NC and Q, and there will be different on N gamma, but still the value is equal to 0. Okay. So then SC we obtain 1.0. So need to rely on the formula as well. Okay. So ultimate bearing capacity CU times NC times CU. This is the CU which is after divide with 1. Okay. So NC 5.14 times SC 1. Okay. Plus 20 times 0.75 times 1.0. So we obtain 162.3. Okay. So ultimate bearing capacity, okay, per meter run. Okay. So we may calculate and determine based on the stress times with the new B prime. So the B prime is 1.3. So then we obtain 220. Okay. Then the last one is to calculate for the bearing capacity, bearing resistance, okay, which is the QU over gamma RV. So the gamma RV is equal to 1. So the value is 220. Okay. So the last one is to get the over design factor, okay, RD, which is the one that we have calculated 220, over FD, okay, which is the total vertical force, 108. So later on, the ratio will become 2.03. Okay. So since the over design factor is greater than 1, the geodynamic state requirement is satisfied. Okay. So so as I told you previously, okay, um, the difference between the what we call it the conventional, okay, we already uh, provide the factor safety, which is 3. Okay, but for this case, the factor we calculate or we obtain after do the calculation, the overall calculation. Okay, so as long it's greater than 1, so it's satisfied. Okay. Okay. Then for the combinations of number 2, okay, okay, so we need to do two calculation, okay, to cope with the combination number 1 and combination number 2. Okay, so the calculation are the same for combination 1, except that this time the following partial factor will be different. Okay, where we have 1.0, okay, 1.3, okay, and for the undrained strength is 1.4, and for the spread footing, okay, if you look on the table, okay, so the R1 is described in the combination number 1, okay, which is 1.0. Okay, so due to the location of the problem is not located at the slope on embankment, so that's why we choose 1.2, 1.4 for the M2. Okay, then repeat the same procedure. Okay, so the new CUD after divide with 1.4 become 21.4. Okay, so WD PD, okay, we obtain 30.650. FD we obtain 80.6. Okay. So then the new B prime is 1.3. Okay, similar with the previous one. Okay. So then do the calculation to get the QU, then we get the RD. 1, after divide with 1, same with the QU. Okay, so the over design factor, okay, is 2.02. Okay, since it's greater than 1, so the geo limit state requirement is satisfied. Okay, so like combination number 2 gives a lower value with the combination number 1. Okay, okay. So that is for the first example. Okay, that is for the undrained or for the clay material. Okay, so now we look on the example 8.6. Okay, for the this time is for the sand. Okay, so a concrete foundation 3 meter wide, 9 meter long, and 0.75 deep is to be founded at the depth of 1.5 in a deep deposit of dense sand. Okay, the angle of shearing resistance of the sand is 35 and its unit weight is 19. Okay, the unit weight of the concrete is 24. Okay, using a lump factor safety approach, which is 3.0, determine the safe bearing capacity for the foundation. Okay, determine the safe bearing capacity of foundation if it's subjected to a vertical line load of 220 kilonewton per meter at the eccentricity of 0.3 meter together with the horizontal line load of 50 kilonewton per meter acting on the base of the foundation as illustrated in figure 8.10. Okay, so this is the situation here. Okay, looks like later on we may assume this is an inclined load because it has a 20 vertical and 50 horizontal. Okay, okay. So then later on we need to calculate based on the based on the by using the Eurocode 7 on situation number 2. Okay. So lump safety factor safe bearing capacity. Okay. So this is the equation that we may use. Okay. So there is no NC because uh, it is there are no because there are no C value. Okay, because it is sand, so no NC in the there are no sub equation number 1. Okay, okay. So only sub equation number 2 and sub equation number 3. Okay, so just repeat the same procedure. Okay, with the P is 35, NC 33.3 and gamma 48.03. Okay, so there we have a SQ, TQ, S gamma, and gamma. Okay, so for the safe bearing capacity for the case number 1, okay, without having any inclination or any eccentricity, so it is equal to 855.7. Okay, so then for the number 2, okay, due to the eccentricity, okay, and the location of and has an inclination of load. Okay, so then we just start to calculate for the safe weight 486 total apply load P equal to 220 times 9 total apply horizontal load. Okay, 50 times 9. Okay, because it is acting on yeah on 9 it is a per meter run. Okay, per meter run. Okay, so that's why 20 times 9. Okay, and then apply horizontal 90 times 9. So total vertical load acting on soil 486 plus 1980. Okay. So then P is given by 180, sorry, 1980. Okay. And then for P plus W is 2466. Okay. The 1980 times 0.3, so the E is less than P over 6 or within the middle third of the foundation. So then the effective width of the footing is the new B prime is equal to 252. Okay. So the foundation is effectively act up upon by a load of magnitude F inclined at the angle of the vertical. So we need to identify what is the alpha, because in the Meyerhof, okay, so we need to uh, determine the alpha, okay, to get the inclined load. Okay, so to identify what will be the inclined load value, so we use the square root v square plus h square. So the value of the inclined load is 250, 2506.7. Then to get the alpha, okay, we use the trigonometry, okay, 450 over 2466 a tangent, then we get 10.3. Okay. So then we just calculate for the IQ, I gamma, SQ, S gamma, DQ, D gamma. Okay. So from just put all the equation, put all the information in the equation, then the value for the safe bearing capacity is 530 kPa. Okay. So that is for the what we call as for the uh, conventional methods. Okay. So now we look on the Euro Code 7. Okay. For the first example, okay, without any eccentricity, okay, weight of the top of the soil, okay, WS 0.75 times 9 times 3 times 19. Total weight of the foundation W for 86 plus 38. Okay, sorry, this is for the inclined problem, because in the question it is already stated here, B, okay, to solve the problem for the second or for the number 2 from the A. Okay. Okay. So then we obtain 348 for the WS and width of the foundation W 870.8. Okay. So by using the combination one, okay, from table, use the same approach, okay, or for the permanent value 1.35 and variable 1.5. Okay, then we have what we call as gamma phi, okay, which is 1, okay, and gamma RV, which is 1.0. Okay, for the design material property, okay, in order to get the phi value, okay, so we need to use the tangent, because when we look on the what we call on let me show you first. Okay, when we look on the uh, table for EC7, okay, so please be careful. Oh, I need to share my slide. Yeah, share this first. Okay. So for the soil, okay, for the phi value, okay. So the actually it is not a straightforward of phi value. So there are tangent there. Okay. So in order to get the phi value to be used for determine the NC and gamma and NQ, so we need to apply the a tangent. Okay. So then divide with 1. Okay. Tangent phi divide with 1. So a tangent to get the phi value. Okay. Okay here. Okay. So then uh 35. I guess the value is still same, 35. Oh, there are no different 35 as well. But the procedure they we need to we need to apply with the tangent because it comes with the tangent. Okay, so tangent 35 over 1. So at the end it will be also become with 35. But when it comes to combination number 2, okay, so the value of this what we call as a phi gamma phi is not 1, it is 1.25. Okay, so there will be a different when we calculate, okay, by using this tangent 35 over 1.25, a tangent again. Okay, so try to use a calculator. Okay, if you miss this calculation, so you just straightforward 35 divide with 1.25. Okay, so what will be the difference? Okay, so we will see later. Okay, on the combination number 2. Okay. So then for the weight of the foundation, because this is a permanent, okay, apply vertical load, permanent horizontal line load is also permanent. So then we obtain, unless in the question it is described, it is a variable load. Okay. So we need to multiply with 1.5. Okay. So then 1175.6 to 673 607.5. Okay. So then the FD we obtain here is 3,848 because this is vertical loads. Okay. So from there we calculate for the eccentricity, the same procedure. Okay. To to get the value for the E. Okay. Then the E um, is within the middle third of the foundation. Okay, so the effective width B 3.2. Yeah, this is the equation. Okay, so we obtain 2.58. Okay, because due to the eccentricity only happen on one direction, so the new area will become 258 2.58 times 9. Okay, 23.2. Okay, so from the table NC, this is the new NC, and we obtain NC and NQ. Okay, so then get the N gamma, SQ, SC, and S gamma. So from here we get the value for the M to be included in the NI. Okay, then M, okay, because it is happen in one direction only. Okay, so then we get the M. So to the I, okay, include I value. Okay, so then we have here IC. Okay, So IQ is 0.74. Okay, we have here H. So H, what we H is the 607.5. Okay, so then we have V here 3848.6. Okay, then plus A. A is the value. Okay, A prime is the value of the effective footing. Okay, 23.2. However, the C is equal to 0 because it is on sandy soil, okay, or drain soil. Okay, so at the end it becomes 0.74. That is for the IQ. Okay, so IC is equal to IQ. Okay, then we just include the IQ 0.74, IQ here, and C46, tangent 35. So we obtain 0.72. Okay. So for the I gamma IQ, M is equal to, where is M? 1.78, 1.78 plus 1 over 1.78, okay, 0.62. Okay. Then ultimate bearing capacity per meter, okay, based on the formula. So NC, no need to have a CD here, no need to have a NC. Okay. So CD is defined as the drain. Okay. So then we just put all the information, then we obtain 1439. Okay, so that is for the QU. Then to get what we call as uh, the the ultimate bearing capacity. Okay, so QU times L times B. Okay, I'm not sure why it used the B, or we call, sorry, the B, not use the B prime. Okay.
Sorry, doctor. This is
Ah,
also for
yeah, sense.
sand soil. Yes.
Okay. B prime, why it not use the B prime here? So in the first one, on the first one, oh, because there is continuous footing. Okay. But sorry, let me look on the first one. Okay, on the first one, he has multiplied with the B prime to get the Q, the load. Okay, however, for this case, I guess actually we need to multiply with the B prime, not the B. Okay. It's supposed to multiply with the B prime. Okay, okay, but it's okay. So 38,89853 divide with 1. Okay, then the overall design factor, okay, where we divide with the bearing resistance over this value. So we obtain 10.1. Okay, it's very big. Yeah, but it's still greater than 1, so it's satisfied. Okay. So then for the combination number 2, okay, as I told you previously, okay, so do you have calculator? Can you just calculate 35 over 1.25? What will be the value? Is it same? 35 over 1.25. We may obtain 28. Okay, so please be careful. Uh, for the material, okay, factor. So we need to use the tangent phi as stated in the table. Do not directly divide with 1.25. Okay? So if we use 28, so we will have a different value for the NC or NQ or NQ and N gamma. Okay, so please be careful. Okay, so 28.3. Okay, then the rest I guess uh, almost similar from what we have discussed. Okay. Okay, then he still use the B, not B prime. Okay. let me check first. Why he use the B, not B prime? Hmm. Because I guess we should use the B prime, okay? Because the B prime is the B effective, okay, to get the ultimate bearing capacity value. Okay, so later on, for the combination number two, okay, the value is 6.19. Okay, so since the over design factor is greater than one, so the geo limit state requirement is satisfied. Okay. Okay, so this is example for non-homogeneous soil condition, which is I not discussed in. There are no example for the EC7. The plate loading test, so you can do a reading on this part, SPT as well. Okay, he also discussed on the correction value, corrected SPT value. Okay, no discussion on the EC7. Okay, so we have two example based on the EC7. Okay, so then this is for the pi foundation. Okay, we take a rest for 5 minutes and then we may continue for the last topic. Yeah, we take a rest until 11:40.